Okay, so today, for homework today, you are taking notes on the first day of functions, our second unit on functions. We've done with matrices, now we're moving to functions. So, here we go. You have two objectives today. We're going to evaluate. So we're going to evaluate functions from tables, graphs, and equations. What is y when x is 1, 2, 3, or 4? The second thing we're going to do is we're going to combine functions using addition, subtraction, multiplication, or division. So first I want to do a quick review of interval notation. A lot of you had it last year, but some of you did not, so I just want to go quick catch that. So a function, we're evaluating functions, is a correspondence between two sets, the x's and the y's, right? Where each element of the first set, the x values, is called the domain. That every element in the domain corresponds to exactly one element in the second set, the y values, called the range. And we know this, that something is a function when it passes the vertical line test, right? That's kind of what you're probably thinking of when you read that. Okay, so when calculating the domain of a function, there are primarily two constraints. I sometimes call them flags or problems to consider. So two constraints. Number one, what values of x make the denominator of the function equal to 0? We have to exclude them. The denominator of a function can never be 0. So whatever makes the denominator 0 has to be taken out of the domain. Okay, the second constraint. If there is an even root or radical, and I'll just write this, a root, like the square root of x, that's a root or a radical. The equation under the root sign must be greater than or equal to 0. So this value right here, just this x, must be greater than or equal to 0. Because you can take the square root of 0 and you can take the square root of 4, but you can't take the square root of negative 4. The even root of a negative number is imaginary. The square root of negative 4 is imaginary. All right. By the way, if ever you feel like this is going too fast, you can stop, finish writing, or rewind it and go back. So I'm trying to get this done as quick as I can, so just for everyone's sake. Okay, so in light of these two constraints, two rules, determine the domain of these two functions. All right, so this is the first constraint. What makes the denominator 0? Because the denominator can never be 0. So what values of x must be excluded from the domain? All right, well, this is what we do. We can see that if you make x 3, then that's 0. So the answer is 3 must be excluded. But let's say it's not as apparent. What do? You take the denominator, x minus 3, and you say it can't be 0. And then you solve for x. So x can't equal 3. And that's how you get that. Therefore, the domain of x is all real numbers except 3. Now, the interval notation that I would like to review is like this. I want all real numbers except 3. So what I do is I say soft bracket, negative infinity. It go from negative infinity all the way up to 3 and soft bracket. Soft bracket means, I'm going to write this over here, soft bracket means don't include. If I had had a hard bracket like that, it would mean do include. Do include that number. Okay? So, negative infinity all the way up to 3, don't include it. You take that piece of the number line, unite it with, don't include 3, but go all the way up to infinity. So all real numbers except 3. That's interval notation. Okay, let's keep going. So first constraint was set the denominator equal to 0, solve for x. And you might set the denominator not equal. That's how we did it. All right, set what is the second one is a radical. Set what is under the radical greater than or equal to 0. The function under a root sign must be greater than or equal to 0. Even roots of negative numbers are imaginary. Okay, that was covered above. Therefore, the domain of g of x must exclude what? Well, let's make that, what we do is we set x plus 4 greater than or equal to 0 and say, what is the domain? Subtract negative 4 from both sides. X is greater than or equal to negative 4. So let's write that is the domain. Here we had x doesn't equal 3. Here x is greater than or equal to negative 4. How do I write that? Well, it includes negative 4. So that's greater than or equal to. But it's greater than that too. So all the way up to positive infinity. Now, therefore, the domain of g of x must exclude everything less than negative 4. So it must exclude everything, all numbers, less than negative 4. Okay? Okay. Now, I'd like you to try these two problems. I'll have the answers in class. This is the first constraint. Don't let that denominator equal to 0. What makes the denominator equal to 0? Ask that question and exclude it from the domain. So you kind of set yourself up. X squared minus 4 doesn't equal 0. That's your no domain. So solve that and figure that out. Now here we take what's under the radical and we want it to be greater than or equal to 0. Okay, so go ahead and work those out and correctly write that in interval notation. And then I'd like you to, as part of your homework, to write a sentence or two describing what we've learned today. How do we evaluate the function of a domain? Okay? All right, so you can stop the tape. I'm going to keep going. Okay, this is the second part of our objective for today. We're going to evaluate functions using tables, graphs, and at the bottom here we have an equation. So, here are the problems we're going to do, A, B, C. So I've got these functions at a certain x, g at 3, h at 2, and then I combine them. So the first thing I want to do is I want to evaluate the functions at 2, 3, 2, 2, and 1. All right, I'm going to evaluate those and then it'll be easier to combine them. So let's evaluate all the f's. F at 2, okay? And then what do we want? We want f at 2, that's the same thing. F at 1, okay? So we're going to evaluate those. All right, a table. F at x, when x equals 2, y equals 6, so the function equals 6. When x is 1, f of x is 3. Okay, those are f's. Let's look at how we do a graph. We have g. G is the graph, right? This is the graph. So we need g at 3. G at 3. So we look, when x is 3, what is y? X is 3, y is negative 3. Then what else do we need? G at 2. G at 2. When x is 2, y is, I go down here, but what do I have here? I want to say negative 3, but then I think, oh, what does that open circle mean? Open circle means don't include. It's like the soft bracket. Don't include this number. So where does this function exist when x is 2? It exists right there. So g of 2 is negative 1. Be careful of that. What else? We need g at 1. G at 1. So when x is 1, y is 0. There we go. So g of 1 equals 0. Now let's do h. H. We don't need h at 2. H at 2. We have an equation. How are we going to handle that? Well, go down to the equation. We just plug in 2 for every x. So h at 2 equals 3 times 2x squared minus 5 times 2 plus 1. So 3, 2 squared is 4, minus 10 plus 1, 12. Minus 10 is 2, plus 1 is 3. Okay, so h of 2 is 3. Do we need any more h's? We got an h of 2 there. We don't need an h there. So we're done evaluating the functions at certain x's. So let's now combine them. So we say f2, that's 6, minus g of 3, minus a negative 3, plus h at 2 is 3. So when I'm evaluating this, I'm going to write it again. Minus a negative is plus 3 plus 3. Oh, okay, that's 12. Please write it out so that you don't make mistakes and subtract 3 and then add 3 and get 6. Okay, so h at 2. H at 2 is 3 minus f at 2, 6, and plus g at 2 plus a negative 1. Now this doesn't change the sign. This is just 3 minus 6, which is negative 3, minus 1, right? You can either way add a negative 1 or subtract 1 and you still get negative 4. Okay, now we're going to take 2 times f at 1. So 2, f at 1 is 3 from our list above, plus 3 times g at 1. G at 1 is 0, minus 2 times f at 1. F at 1 is 3. So when we write that, we do the math and we say 6 plus anything times 0 is 0, minus 6. We see that those cancel and I'm left with 0. Okay, what I'd like you to do now is to write, finish the other side, write a summary of how you evaluate functions at tables, graphs, and equations. All right, and I'll see you tomorrow.